Can feedback control systems ignore unexpected disturbances? Imagine you're steering a boat across a lake. You want to stay on course, but suddenly a gust of wind pushes you off path. Can your steering system just ignore that gust? Not quite. Feedback control systems are designed to detect and respond to disturbances, not ignore them. They constantly measure the output, like the boat's position, and compare it to where it should be. If there's a deviation caused by a disturbance, the system adjusts the input, such as the steering angle, to bring things back on track. In electrical engineering, this process is used in many devices. For example, in motor speed control, feedback helps keep the motor running at a steady speed even if the load changes unexpectedly. The system detects the change and corrects it by adjusting the power input. But it's important to understand that feedback control can't completely ignore disturbances. It can reduce their impact, especially those that happen slowly or at low frequencies. When disturbances are at high frequencies or sudden, feedback systems might struggle. They might even amplify these quick changes, leading to oscillations or noise. This is because of how the system responds to different frequencies, which is described by what is called the sensitivity function. The better the controller is tuned, the more effectively it can reject disturbances. Controllers like proportional integral derivative controllers are common because they help eliminate steady errors and respond quickly to changes. However, no control system is perfect. Unexpected or high-frequency disturbances can still cause issues. If the controller gain is set too high, it might cause the system to overshoot or oscillate. Actuator limits and nonlinearities in the system also affect how well it can reject disturbances. To handle this, engineers often combine feedback control with feedforward control. Feedforward anticipates disturbances and adjusts the input before the disturbance even affects the system. Power plants, manufacturing lines, and even electric vehicles use feedback control systems to stay stable despite disturbances. For example, in electric motor drives, feedback helps maintain speed when loads vary. Power systems use feedback to keep voltage and frequency steady even when demand fluctuates. So, in the end, feedback control systems do not ignore unexpected disturbances. Instead, they are built to detect, minimize, and respond to them as best as they can, depending on how they are designed and tuned.